Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Thank you so much for having me. I'm really excited to get into this today.
Yeah, we have a massive topic. So I want you, the listener right now, to just imagine something for a second. Imagine you are tasked with designing, like, the world's most advanced aerospace component.
Right. High stakes.
Exactly. And your company is prepared to spend just a massive amount of capital on the absolute best CNC machines, the most highly trained floor technicians, and the most optimized assembly lines the industry has ever seen.
The dream scenario for any manufacturing firm, really.
Yeah, right. But now, imagine finding out that before a single piece of titanium is ever cut, before the very first spindle even turns on the factory floor, 80% the final manufacturing cost of that product has already been permanently locked in by the design team.
It's a tough pill to swallow, but it is entirely accurate.
It's crazy. So today, we are opening the doors to a masterclass on how to fix that exact problem. If you are listening to this, consider yourself enrolled in a deep dive into the real mechanics of engineering efficiency.
I love that framing. It really is a masterclass.
And to set the exact right mood for what we are about to undertake, I am looking across the studio right now at our expert guide, whose backdrop has just visually transformed into something incredible.
It's pretty cool, isn't it?
It's amazing. We have this whole aesthetic going on. It looks like a classic mid-century engineering drafting room. We've got the wooden tilt desks, the T-squares, the vellum paper. But it's completely overlaid with these sleek, modern, glowing, holographic 3D models just spinning in midair.
Yeah, it really is the perfect visual. What you're seeing behind me is, well, it's a blend of foundational, timeless engineering discipline colliding with the absolute cutting edge of digital integration.
It's the perfect vibe for this.
Right, because today we are going to explore the vast, incredibly powerful, and frankly, deeply misunderstood world of lean engineering.
Yes. And we have a very specific mission for this deep dive. First, we're going to break down what lean engineering actually means, because it's really not what most people think it is.
Not at all. There's a lot of baggage with that word.
Totally. Second, we're going to get into the weeds of the biggest pain points, like the real implementation nightmares that working engineers face when they actually try to bring these concepts into their daily workflow.
Which is where the real struggle happens.
Yep. Third, we're going to dispel some massive industry myths that just keep manufacturing companies stuck in the past. And we'll wrap it all up by tackling the most pressing, hotly debated questions engineer professionals are arguing about online right now.
That roadmap is exactly what we need because to establish our baseline right here at the start, I really want to clarify the reality of what we are dealing with. There is so much noise out there.
Oh, an unbelievable amount of noise.
Right. When most people hear the word lean, they instantly picture a factory floor. They picture like a guy with a stopwatch yelling at assembly line workers to move their hands faster.
Right. Yes. That's exactly the image, just sweating and working faster.
Right, but that is a colossal misconception. True lean thinking is an entire holistic life cycle philosophy. It is a system designed from the ground up to eliminate waste and to elevate customer value.
And that starts way before the factory floor, right?
Exactly. That process begins from the very first blueprint, the very first CAD sketch. It is about creating the right products, doing the right thing right, and utilizing highly efficient engineering processes to actually get there.
Okay, let's unpack this immediately, because that 80% statistic I threw out in the intro is still kind of blowing my mind.
It usually does shock people the first time they hear it.
Well, yeah.
Yeah.
Because before we can start looking at the real-world pain points, like the spectacular failures and the massive successes of implementing lean, we really have to understand the anatomy of a product's life cycle.
Right, you have to look at the whole picture.
Exactly. It's like, well, engineering is exactly like writing the DNA for a living organism. If the DNA itself is inefficient, if it has genetic flaws baked into the code from day one, no amount of a good environment is going to save it.
That's a perfect way to look at it.
Right. Like, no amount of brilliant, highly optimized downstream manufacturing is ever going to fix flawed DNA. You are literally just manufacturing a flawed design really, really efficiently.
That is precisely the right way to frame it. You simply cannot manufacture your way out of a bad design. And the data backing up your DNA analogy is just staggering.
So where does that 80% number come from?
Well, in the industry, we refer to this early stage as the fuzzy front end of product development,
Hmm.
and that statistic is the defining rule of the fuzzy front end.
Okay.
80% of a product's total cost is permanently dictated by the engineering design phase alone.
I I have to push back on this, or at least ask you to break it down,
Well,
because how is that actually possible?
I get this pushback all the time.
Well, if the manufacturing floor is where all the physical labor happens,
Yeah.
right? Where all the energy is consumed, where the huge metal is being shaped, how is the engineering department sitting in an air-conditioned office dictating 80% of the cost?
Because the engineers are making decisions that force the factory's hand. They drive the costs through several primary avenues. Let's start with the most basic one. The sheer number of parts and the tolerances required.
Okay, that makes sense.
If you, as a design engineer, create a housing that requires 50 intricate parts with incredibly tight tolerances, you have just guaranteed high manufacturing costs.
Because they have to actually make those parts.
Exactly. The factory has absolutely no choice but to machine those 50 parts to your specific spec. Second, think about the assembly technique.
Right.
The design engineer is the one who decides if this product will be put together using traditional mechanical fasteners, like, say, hundreds of tiny screws, or if it will utilize a totally different approach, like electron beam welding or maybe co-curing composites.
Oh, wow. Yeah, that makes total sense. If I design something that needs 100 tiny screws, instead of a snap fit design or like a single welded seam, I am physically forcing the factory to spend time, labor, and machinery turning 100 individual screws. My CAD model just dictated their labor costs.
That's exactly it. You locked in their workflow.
What else drives that 80%?
The manufacturing processes themselves. You, the engineer, decide whether a part needs to be heat treated or maybe shot peen for fatigue strength or anodized.
And each of those is a separate step.
Right. Each callout on your drawing adds a physical routing step in the factory. And finally, the tooling approach. Are we going to need matched metal dies? Are we using custom injection molding?
Oh, and those molds are incredibly expensive.
Exactly. The moment the engineer signs off on those specifications, the factory has to spend the capital to execute them. They have to go buy the molds. They have to buy the heat treating ovens.
It's basically a massive shopping list the factory has no choice but to pay for.
Precisely. This is exactly why those early decisions are so critical and why a disciplined, lean systems engineering process at the very beginning is absolutely essential to survival.
So if the stakes are truly that high, if the financial destiny of the company is essentially locked in by the time the CAD files are actually released, how do we ensure that the DNA is written correctly?
It takes a big shift in mindset.
Like, how do we physically stop engineers from designing overly complex, expensive nightmares?
To write good DNA, we have to fundamentally shift the philosophy of the whole engineering department. The driving force behind integrating lean efforts across an enterprise relies on James Womack and Daniel Jones's 5 basic principles of lean thinking.
Okay, the 5 principles.
These are the absolute bedrock of everything we will discuss today, and we really need to understand the mechanics of each one.
Let's do it. What is principle number 1, and how does it actually play out in a modern engineering environment?
Principle 1 is specify value. Now, the crucial caveat here, and this is the part that engineers often struggle with, is that value is defined solely by the ultimate customer.
Solely by the customer, not the engineer.
Exactly. It is not defined by what the engineering team thinks is cool, or what the marketing department assumes is trendy, or what management just wants to push out the door to meet a quarterly quota.
Right.
A product only shows value when it satisfies the customer's specific needs at a specific price point and at a specific time.
I've seen this go wrong so many times.
Oh, it happens constantly.
You get an engineering team that gets completely obsessed with a new technology. They spend, like, 6 months and endless resources engineering a highly complex, connected Bluetooth feature into a product.
Yep, I know exactly where this is going.
Right, only to launch it and realize the customer literally just wanted a physical button that worked reliably. From a lean perspective, all that brilliant Bluetooth engineering was just pure waste, wasn't it?
It absolutely was. It doesn't matter how elegantly you design that Bluetooth feature. If the customer won't pay for it, it is waste. Which brings us to principle 2. Identify the value stream.
Now, I want to stop you right there, because value stream sounds like serious corporate buzzword bingo.
It does sound like consultant speak, I admit.
Right. So for the listener who is just trying to get their CAD models approved by their boss, What does mapping a value stream actually look like in an office? Are we physically tracking how many times a file is emailed?
In a way, yeah, you actually are. Identifying the value stream means you meticulously map out every single action, process, and handoff required to bring a specific product from a conceptual idea all the way to a physical launch.
So mapping the whole journey.
Right. In an office environment, this means mapping the flow of information. You literally chart out, okay, I finished the CAD model, then it sits in a server waiting for an FEA simulation.
Right.
Then the simulation engineer emails it back with corrections, then I fix it, then it goes to the chief engineer for a signature, then it waits 3 weeks for a committee review.
Oh man, that 3-week wait is painfully accurate.
It is. By mapping this entire life cycle, you start to see which steps actually create value, like the actual designing and testing, and which steps are just bureaucratic waste.
It's like pulling the curtain back on the invisible office machinery.
Exactly.
Okay, so once you see the map, what do you actually do with it?
That leads to principle 3. Make value flow. Once you have your map and you've identified the obvious waste, your job is to ensure the remaining value-creating steps flow continuously.
Meaning no roadblocks.
Right. You want to execute the project without interruptions, without massive batching of work, and without huge waiting periods between different departments.
Now, what does batching mean in the context of an engineering office? Because obviously we aren't batching physical metal parts in a bin.
Right. Batching in engineering often looks like waiting to send a dozen drawings over to the checking department all at once on a Friday afternoon, rather than sending them one by one as they are actually finished.
Oh, I've been guilty of that.
We all have. But when you batch like that, you create a massive traffic jam for the next person in line. Flow means smoothing that out.
Okay, that makes total sense. Don't dump work on people. What's principle 4?
Let the customer pull value from the producer.
Cool value.
Okay. Yeah. In a traditional system, you forecast what you think the market wants, you design it in a vacuum, and you just push it onto the market.
Hoping they buy it.
Right. A pull system synchronizes your flow so that you are designing and building in direct response to actual customer demand or the direct needs of the next downstream internal customer.
So you aren't doing work just to do work.
Exactly. You only do the work when it is signaled that the work is needed.
And the final principle, which honestly always sounds to me like an unattainable Zen state that companies just put on a motivational poster in the break room.
Yeah, principle 5. Pursue perfection.
There it is.
It sounds lofty, but it is the vital recognition that Lean is not a project you finish.
It's not just checking a box.
No, it is not a software you install and then you're done. It is a continuous, never-ending cycle of improvement. You map the value stream, you create flow, you establish pull, and then you look at the system again and say, okay, where is the next layer of waste?
Always finding the next bottleneck.
Right. Yeah.
So if we are supposed to be pursuing perfection and making value flow, I think we need to take a really hard, honest look at what is actually happening in the fuzzy front end right now.
We definitely do.
Because the reality of the engineering office is usually a million miles away from perfect flow. Let's talk about the 8 wastes of engineering.
Yes, let's get into the wastes.
Because we always hear about waste on the factory floor, right? Scrap metal in the bins, machines leaking oil, forklifts just driving around empty. You can literally point to it.
It's very visible.
Right. But waste in an office environment is incredibly well camouflaged. It just looks like smart people staring intensely at computer monitors.
That is the exact danger. Office waste doesn't look like waste. It looks like busy work. So let's break down the 8 engineering wastes.
All right, what's number 1?
Number 1 is overproduction. In a factory, this is making 1,000 extra car doors that no one actually ordered.
Okay.
But in engineering, overproduction is generating massive amounts of analysis, writing 100-page reports, or running extensive tests that are simply not needed, not asked for by the customer, and not utilized by the downstream manufacturing team.
Oh, man. I've witnessed this firsthand.
I'm sure you have.
You have a highly capable engineer who spends 3 weeks perfecting a computational fluid dynamics simulation for a thermal load case that will literally never happen in reality.
Yes.
And they do it simply because the software allows them to do it and because they personally find it intellectually interesting. Like, it's beautiful work, but it adds 0 value to the product.
Precisely. It is a total drain on resources.
Yeah.
And that leads directly to waste number 2, inventory.
Now, in an office, inventory isn't a warehouse full of boxes gathering dust.
No. In an engineering department, inventory is unfinished analysis. It's half-written technical reports.
Oh, like CAD files just sitting on a hard drive.
Exactly. It's untested prototype software code sitting in a repository. It is a brilliant CAD assembly sitting on a local hard drive waiting for a review. It represents invested time and money that hasn't delivered any actual value to the customer yet.
It's locked up intellectual capital.
Completely.
Wow. Okay. Waste number 3 is transportation. Now, obviously, we aren't talking about forklifts moving pallets of drawings around anymore.
No, in the engineering value stream, transportation waste is all about the routing of information. It's the complex, convoluted handoffs.
Like email chains.
Exactly. It is sending a design file to 5 different departments for validation, requiring multiple physical or digital signatures, and moving data across incompatible software platforms where someone has to manually re-enter numbers.
Oh, the manual data entry. That's the word.
It is. Every single handoff is an opportunity for human error, data corruption, and massive delay.
Which feeds perfectly into waste number 4, which I think is the absolute bane of the modern knowledge worker. Unnecessary movement, or as the literature calls it, stop-and-go tasking.
This is the absolute killer of engineering productivity. Unnecessary movement in the office happens when engineers are forced to juggle too many projects at one exact time.
Oh, yeah.
We've all been there. You start a complex CAD task, you get into a flow state, and then you have to stop to answer an urgent email about a totally different project.
Right.
Then you get pulled into a 1-hour meeting for a third project. When you get back to your desk, you spend 20 minutes just trying to remember where you were on the first task.
The cognitive switching costs are immense.
They are immense, and they are pure waste.
And while they are constantly switching gears, they are almost certainly dealing with waste number 5, waiting.
Waiting is a massive, silent drain on resources.
Just sitting around.
Right. Waiting for management to approve a budget, waiting for a supplier to send a specification sheet, waiting for the results of a physical test from the lab.
Yeah.
If a highly paid engineer cannot proceed with their primary task because they are waiting on a gatekeeper, that time is evaporating.
Is it gone forever?
Exactly. And the remaining 3 wastes are just as insidious. There is processing waste, which is doing things the hard, manual way instead of using standardized tools or macros.
Right.
There are defects, which in an engineering context means erroneous calculations, bad drawings, or defective enterprise decisions that lead to massive downstream rework. And finally, underutilizing human potential.
Which might be the saddest one.
It really is.
Okay, so when you take all of those invisible office wastes, the overproduction of analysis, the massive inventory of unreleased files, the constant stop-and-go task switching, and the endless waiting on approvals, what does the actual data look like?
It's pretty grim.
Because this is where my jaw hit the floor when I was reviewing the source materials for this deep dive.
The data is shocking, and it should be a wake-up call for every engineering manager out there. According to extensive studies and opinion surveys conducted in workshops across the aerospace and automotive industries, a staggering 40% of product development effort is considered pure waste.
40%.
40%.
Almost half of the mental effort, the time, and the salary of these highly trained professionals is just completely evaporating into the ether. It's producing nothing.
It actually gets worse.
Oh, no.
Yeah. Another 29% of their effort is considered necessary waste.
Necessary waste, what does that mean?
These are things you have to do because of current system limitations, like filling out mandatory compliance forms or navigating broken legacy software, but they don't actually add any direct value to the product.
Okay.
But here's the most damning statistic. When researchers studied detailed member companies, they found that 62% of tasks are sitting idle at any given time.
62%.
Right. In Kaizen-type continuous improvement events, they routinely find that task idle time runs between 50 and 90%.
Okay, I want you, the listener, to really stop what you're doing for a second and reflect on your own workday. Think about your last 40 hours in the office. How much of your time was actually spent creating the DNA of the product? Like doing the core engineering, the deep problem solving, the actual design work that directly translates to customer value.
It's a sobering thought.
Right. And how much of your time was spent waiting on an email reply, waiting for a committee to make a decision, untangling a complex handoff, or sitting in a meeting that literally didn't pertain to you? Because statistically, 62% of your tasks are just sitting there, idle, trapped in the system.
And that is exactly why we cannot just tell engineers to work harder.
You can't outwork that.
No, you cannot work a system where tasks are idle 62% of the time.
That-
We have to fundamentally restructure the workflow to eliminate that idle time.
Okay, so if 62% of an engineer's day is evaporating, the system itself is broken. We clearly need a new approach. So how does a modern lean engineer actually go in and physically restructure an office workflow?
Well, we have to look at the tools.
Right, let's open up the lean engineer's toolbox and look at the cure.
To understand the cure, we first have to look at the profile of the person wielding the tools. The modern lean engineer is not the traditional industrial engineer of the 1950s who just walked around with a clipboard and a stopwatch.
Right, the guy with the pocket protector.
Exactly. The modern lean engineer has a foundational bedrock in traditional industrial engineering understanding probability and statistics, operations research, ergonomics, and time and motion studies.
But it goes further than that now.
It is vastly enhanced. They are equipped with advanced Six Sigma capabilities. They utilize tools like design of experiments, Taguchi methods, and gauge R&R to brutally eliminate variation and defects from the design process itself.
Whoa, stop right there.
Too much jargon.
You just threw a lot of heavy statistical jargon at me and the audience. Taguchi methods. Gauge R&R.
Fair enough.
For the design engineer listening right now who spends all day in CAD and hasn't taken an industrial stats class in 10 years, we really need to translate this.
Yeah.
What does gauge R&R actually mean in plain English? And why does a design engineer care?
That is a very fair point. Let's demystify it. Gauge R&R stands for gauge repeatability and reproducibility.
Okay.
In plain English, before you can trust any data, you have to know if your measuring tool is lying to you.
Lying to you.
Yeah. Imagine you and I are both measuring the same piece of machined metal with two different sets of calipers. If we get different numbers, is the part physically defective or are the calipers just uncalibrated?
Right.
Or do you just squeeze the calipers harder than I do?
Oh, operator error.
Exactly.
Mhm.
Gauge R&R is a statistical tool that tells you how much of the variation in your data is coming from the actual product and how much is just error from the measuring system or the human operator.
That is brilliant.
Lean engineers use this to ensure they are making decisions based on reality, not on bad measurements.
Okay, that makes perfect sense. Because if your ruler is broken, all your math is useless.
Exactly.
What about Taguchi methods or design of experiments?
Design of experiments, or DOE, is a way to test multiple variables at the same time to see how they interact. Instead of changing one thing at a time, which takes forever, you set up a structured matrix of tests.
So it's way faster.
Yes. It lets you find the absolute optimal settings for a process with the fewest number of physical tests. And Taguchi methods are all about robust design.
Robust design.
Right. Junichi Taguchi realized that you can't always control the manufacturing environment perfectly. So instead of trying to force the factory to be perfect, you engineer the product's DNA to be so robust that it still works perfectly, even if the manufacturing process fluctuates slightly, or if the customer uses it in extreme temperatures.
So it's like engineering a suspension system that rides smoothly whether you are on a freshly paved highway or a bumpy gravel road. You are designing immunity to variation directly into the product.
That is a fantastic analogy. Exactly. And crucially, modern lean engineers also incorporate green engineering tools.
Like sustainability.
Yes, environmental design, energy-efficient design, and remanufacturing concepts. The ultimate goal is to take the manufacturing plant to zero waste going to the landfill while making things cheaper, better, and faster in a highly flexible way.
It's a super hybrid skill set. They're optimizing for speed, for perfect quality, and for zero environmental impact simultaneously.
It's a tall order, but it's entirely possible.
And to see how this incredibly potent skill set actually restructures a workflow in the physical world, our source materials point us to the legendary origin point of all of this, the Toyota production system.
Yes. Toyota, largely led by Paiichi Ono, didn't just tweak American mass production, they completely inverted the philosophy.
How so?
They looked at the traditional mass production system, where you make massive batches of identical parts, store them in huge inventory warehouses, and push them down a rigid, never-stopping final assembly line, and they realized it was fundamentally fragile and wasteful.
Because if one thing goes wrong, the whole line is stuck.
Exactly. Mass production was built entirely on the economy of scale. Toyota shifted the paradigm to the economy of scope.
Okay, how does the economy of scope actually physically manifest on a factory floor? Like, what does it look like to walk through?
They changed the final assembly line into a mixed model final assembly cell. Instead of massive, mile-long, straight conveyor belts, they designed manufacturing cells, often U-shaped, to enable one-piece flow.
One-piece flow.
Right. In a mixed model cell, you might see a red sedan, followed immediately by a blue truck, followed by a silver hatchback, all coming down the same line.
That sounds chaotic.
It looks complex, but it's highly orchestrated, and the entire system operates on a critical concept called takt time.
Takt time. That is a word that gets thrown around a lot in management meetings. It's essentially the heartbeat of the factory, right?
It is exactly the heartbeat. Takt is a German word for rhythm or meter. Takt time is the precise rhythm of customer demand.
Okay, so how do you find that rhythm?
You calculate it by taking your available working time and dividing it by the number of units the customer actually ordered.
Got it.
If the math dictates that the customer is buying one product every 10 minutes, the entire factory must be synchronized to produce one product exactly every 10 minutes. Not faster, not slower.
Wait, not faster. Why wouldn't you want to go faster?
If you go faster, you are creating overproduction waste. You're building inventory you don't need.
Oh, right.
And if you go slower, you're failing the customer. To achieve this perfect heartbeat, the work cells operate on a principle called Moko-Mo.
Moko-Mo. Make one, check one, move one on.
Precisely. You make a single part, you immediately verify its quality, and you pass it directly to the next step. There is zero batching.
No piles of parts waiting around.
None. But to make the check one part possible without completely stopping the heartbeat of the line, lean engineers use single-cycle machine tools equipped with built-in error-proofing devices. These are called Poka-Yokes.
Poka-Yokes. I love that term. Give me a tangible engineering example of a Poka-Yoke.
Think about a simple USB plug. The older USB-A cables were designed so they physically could only be plugged in one way.
Oh, yeah. You always try it the wrong way first.
Right. The plastic block inside prevented you from inserting it upside down. That physical geometry is a Poka-Yoke.
So it forces the correct orientation.
Exactly. In a factory, it might be a fixture that has a pin in it, so a piece of sheet metal can only be loaded into the stamping press in the correct orientation. It is a physical or digital safeguard that makes it physically impossible for a worker to pass a defective or improperly oriented part forward.
That is so smart.
Furthermore, they use devices called decouplers between machines to assist the standing, walking workers producing the parts, ensuring the flow literally never stops.
Okay, here's where it gets really interesting, and I want to push back on this philosophy hard.
All right, let's hear it.
Because I can hear the design engineers listening right now getting very nervous. If we are putting our engineers and our floor workers on these rigid tracks, operating to a strict mathematical heartbeat, utilizing built-in Poka-Yokes so they don't even have to think about orientation, and enforcing standard work rules, aren't we just creating template engineers? Are we stripping the art, the intuition, and the creativity out of the engineering process by turning the office into a rigid concurrent assembly line?
It is the most common fear when lean is brought into an R&D environment.
It's a valid fear.
But the source material explicitly identifies this as myth number 3, and it debunks it completely. The myth is that real-time concurrent engineering is dangerous because it creates template engineers who just blindly follow rigid rules. The reality is the exact opposite.
How so? How does standardizing the work and enforcing a heartbeat increase creativity? That seems super counterintuitive.
Because true concurrent engineering, especially on highly complex projects, demands significantly more human intuition and creativity, not less. The documentation notes that attendance at a real-time concurrent engineering design session proves instantly that there is nothing automatic or templated about designing a highly customized, multi-million-dollar piece of aerospace technology.
It's still hard problem solving.
Exactly. Think about the cognitive switching costs we discussed earlier. When you strip away the waste, the waiting, the searching for lost files on a server, the endless email chains trying to get an approval, you aren't left with an empty void.
Right.
You are left with pure, unadulterated time to actually think. By standardizing the mundane, repetitive tasks, you free up the incredible processing power of the human mind to tackle the complex, novel problems that a machine, a software, or a template can never solve.
You're removing the friction.
Right. You simply cannot automate the creative leaps required to design a modern commercial aircraft.
Speaking of aircraft, I want to share one of the most incredible real-world success stories from our sources today. This is the tale of the Boeing floor beams.
Oh, this is a phenomenal case study.
It perfectly illustrates what happens when you take these lean tools, specifically variability reduction, standard work, and lean engineering design, and apply them to something absolutely massive.
The transition in design philosophy from the Boeing 747 to the Boeing 777, it is a textbook example of lean engineering fundamentally changing the entire financial landscape of a product.
Right. So let's look at the old way. On the Boeing 747 commercial aircraft, the assembly strategy for the massive floor beams relied heavily on what we call hard tooling. They used 28 hard tools and 2 soft tools per part number.
Which is incredibly rigid.
Yeah. The assembly process was incredibly convoluted, involving 10 major assembly steps. And the process capability, the statistical measure of how well the manufacturing process stays within the design limits, was incredibly low.
Yes, the source notes that the creepit was less than 1, representing roughly a 3 sigma level of quality. That means there was a massive amount of variation in the parts being produced.
Okay, proxy for the audience again. Can we translate CPT for the engineer who spends all day in SolidWorks and maybe doesn't run statistical process capability studies? What does a key peak of less than 1 actually mean on the factory floor?
Key peak is essentially a score of how well your manufacturing process fits within the tolerance limits you designed.
Okay.
Imagine parking a car in a garage. The tolerance limits are the walls of the garage. The car is your manufacturing process.
Right.
A high C-peak means you are driving a very small car perfectly down the center of the garage every time. Plenty of room on both sides.
Safely parked.
Exactly. A C-peak of less than 1 means you are driving a massive SUV and you are constantly scraping the side mirrors against the walls. The variation is just too wide for the tolerance limits.
That's a great visual. And because there was so much variation in how those 747 parts were made and how they fit together, when the technicians finally went to assemble the floor beams on the aircraft, nothing lined up perfectly.
Right. The SUV scraped the walls.
Exactly. So they had to use shims. For those who might not be familiar with aerospace assembly, a shim is essentially a small, custom piece of material you wedge into a gap between 2 poorly fitting parts to make them sit flush so you can bolt them together safely.
It's a Band-Aid.
Yeah. And on the 747, they had to use 18 shims per floor beam assembly. 18. Just to make the plane structurally sound.
Which is a massive amount of hidden waste. Think
Yeah.
about the manual labor involved there.
It's all manual rework.
Right. Fitting 18 shims requires a highly skilled technician to measure the specific, unique gap on that specific airplane, custom cut a piece of material, install it, check the fit, and probably take it out and adjust it.
Over and over again.
It is pure, unadulterated manual rework on the final assembly line, simply because the DNA of the design and the variation in the manufacturing process were flawed from the start.
Enter lean engineering on the Boeing 777 program. They completely rethought the entire assembly strategy. By rigorously applying lean principles and 3D digital design, they moved to a toolless assembly strategy. They went from 28 hard tools down to 0. 0 hard tools. They streamlined the major assembly steps from 10 down to 5.
And look at the results on the metrics that actually matter to the bottom line. Process assembly hours dropped to 47% of what they were on the 747.
Wow.
They literally cut the labor time in half. The process capability, that TreePick metric we just defined, skyrocketed to greater than 1.5, which is a 4.5 sigma level of quality.
So the car shrunk.
Yes. The variation was nearly eliminated. The car was now driving perfectly down the center of the garage every single time.
And here's the mic drop moment.
Yeah.
The number of shims. They went from 18 custom shims on the 747 down to exactly 0 on the 777. 0 shims.
That's just incredible.
The parts were designed so intelligently, and the manufacturing variation was so tightly controlled that the massive components simply fit together perfectly every single time. That is the sheer power of a lean engineering mindset.
It is a profound philosophical shift. They moved from a culture of inspecting and shimming in quality at the end to a culture of designing and building in perfect quality from the beginning.
It's beautiful.
And it proves definitively that lean isn't just a manufacturing trick to speed up assembly lines, it is an engineering triumph.
Okay, but this incredible success story brings us to a harsh reality check.
There's always a catch.
Right. If these tools are so incredibly effective, if they can cut assembly time in half, completely eliminate custom shims on a commercial airliner, and drastically speed up development, why do so many companies fail spectacularly when they try to implement them? Why isn't every engineering firm operating like the Boeing 777 team?
Well, because implementing lean is fundamentally a psychological and cultural transformation, not just a mechanical one. The biggest barrier to entry is what the literature calls the program of the month syndrome.
The dreaded POM. We have all lived through this.
Yes. When lean is first introduced in a facility, the immediate visceral reaction from the workforce is usually fear, followed quickly by deep cynicism.
Definitely.
Workers instantly fear for their livelihoods. They hear management use the word efficiency, and they immediately translate that to layoffs.
Right. Efficiency means I'm losing my job.
Exactly. They ask, does this new system mean my job is in jeopardy? And concurrently, they look at management's historical track record and say, how do I know this isn't just another flavor-of-the-month management fad that will completely disappear in 6 months when the executives get bored?
And honestly, can you blame them?
Not at all.
If an engineering company has a long history of launching initiatives with big kickoff meetings, printed banners, and catered lunches, only to quietly abandon the entire system when the end-of-quarter numbers look a little tight.
It happens everywhere.
The employees have been systematically trained to be cynical. They just keep their heads down and wait for the fad to pass.
Exactly. The source material is very clear on this. If that is the history of the company, there is no dodging the issue. It has to be dealt with squarely, honestly, and upfront.
So what does the leadership actually do?
The lean implementation coordinator has to painstakingly explain to the workforce that true lean, with its emphasis on pull systems and operating at tack time, is about securing the long-term financial viability of the company, which secures jobs.
It's about survival.
Right. It is not about short-term headcount reductions to boost a quarterly report, but achieving that requires immense trust, which is almost always lacking at the start.
I want to introduce a powerful analogy here that really clarifies why so many of these massive corporate initiatives collapse under their own weight. Think about trying to calibrate a high-end 5-axis CNC machine.
Okay.
Implementing advanced lean flow before establishing your basic operational definitions is like writing a brilliant, highly complex G-code program for that CNC mill, but completely failing to notice that the machine's physical bed is out of frame by half an inch.
That's a fantastic way to visualize it, because what happens when you hit start?
You crash the tool.
Exactly.
The code, the lean initiative, is brilliant. It's theoretically perfect. But because the foundation, the operational definitions, the basic standard work is crooked and misaligned, you are just going to destroy your equipment.
The foundation has to be level.
In lean engineering, your operational definitions are things like clear work instructions, updated training matrices, visual displays, and standard operating procedures. If you don't clean up that foundational bed first, before you try to implement advanced, highly synchronized flow concepts, you're just guaranteeing massive rework. You are going to crash the company.
It is a tragic waste of your most precious commodity. The thinking, problem-solving minds of your engineers.
Completely.
The foundational precursors absolutely must be addressed first. In fact, the research highlights 10 specific common reasons why lean initiatives fail, either in part or totally. And most of them tie right back to trying to run perfect code on a crooked machine.
Let's walk through some of the heavy hitters on that list of 10. Where do companies stumble the hardest?
One of the most critical points of failure is management failing what is called the commitment test.
The commitment test.
This means that the executive team likes the idea of lean. They like the PowerPoint slides showing cost reductions. But they aren't willing to make the hard, painful sacrifices required to actually support it.
Right. They won't write the checks or give people the time.
Exactly. They don't provide the dedicated time, the financial resources, or the unwavering leadership focus required to change the culture. Another major reason is an inadequate understanding of process management. Specifically, management not understanding what process stability actually is, what process capability means, or how to identify and relieve bottlenecks.
What about external factors? Because I see a lot of companies implement these systems, fail, and then instantly point the finger at their supply chain.
Yes, unreliable raw material suppliers is firmly on the list of failure.
Of course.
If you are trying to operate a synchronized, just-in-time pull system where parts arrive exactly when you need them and your supplier is constantly late or they are delivering defective batches, your entire synchronized flow collapses immediately.
It's a chain reaction.
It is. Lean requires treating suppliers as heavily integrated, certified partners, not just adversarial vendors that you squeeze for the lowest possible bid.
That makes a lot of sense.
Another massive reason for failure is an inadequate understanding of variation and its compounding effects. If management doesn't understand statistics, they will make disastrous knee-jerk decisions.
Let's talk about variation for a second.
Yeah.
When we say management doesn't understand variation, what does that actually mean in a day-to-day context?
It means they overreact to normal statistical noise.
Oh, I've seen this.
If a process naturally varies by plus or minus 2 millimeters, and one day a part comes out 1 millimeter off center, a bad manager will stop the line, yell at the operator, and force them to adjust the machine.
Right. Fix it immediately.
But the machine was operating perfectly within its normal statistical variation. By adjusting it, the manager has now actually induced more error into the system. It's called tampering.
Wow.
Without an understanding of statistics, management becomes the root cause of the defects.
And reason number 10 ties right back to our CNC machine analogy. Failing to properly address the 5 precursors to lean.
Right.
If the foundational issues like workplace organization, visual management, and total productive maintenance aren't built into the implementation plan at the proper rigorous sequence, the entire initiative will inevitably crumble.
Let's dig even deeper into the actual messy mechanics of problem solving during these implementations. One of the core non-negotiable concepts of lean is jidoka.
Jidoka.
Jidoka roughly translates to automation or building quality into the process. Crucially, it means having the authority and the discipline to stop the line to fix problems as they occur, rather than letting defects pass downstream.
Stopping the line is terrifying for management.
It is. The literature notes that quality problem solving, which is the engine of jidoka, is often a major crippling weakness in corporate implementations.
But why? I mean, engineering firms are literally buildings full of professional problem solvers. Why is fixing quality problems so hard for smart companies?
To answer that, the source material uses a classic lean diagnostic tool, the 5 whys.
Oh, I love the 5 whys.
You ask why, sequentially, to drill down past the superficial symptoms to the actual root cause. So why is jidoka a weakness? Because quality problem solving is incredibly hard to do in practice.
Okay, why is quality problem solving hard to do?
For a cascade of interconnected reasons. First, basic human nature. We tend to instinctively avoid problems or hide them rather than embrace them as golden opportunities to improve the system.
Because nobody wants to be the one who made the mistake.
Exactly. Second, the organization often lacks a sound, deeply ingrained continuous improvement philosophy. It's treated as an afterthought.
Okay, what's third?
Third, the workforce itself may simply lack the specific analytical skills like root cause analysis or statistical process control required for complex problem solving.
They just don't have the tools.
Right. Fourth, and this is usually the biggest hurdle, management physically doesn't give them the time to work on problem solving because everyone is too busy fighting the daily fires caused by the broken system.
Oh man, they're too busy bailing water to fix the leak.
Exactly. And finally, even if you have the time and the skills, the data available is often so poor or corrupted that you can't actually solve the problem.
That is a brutal, self-reinforcing cascade of failures. We instinctively hide the problem. We don't have the corporate mindset to fix it. We haven't trained our people on the analytical skills. We don't give them the time to think. And our data is garbage anyway. No wonder jidoka fails.
It's a perfect storm.
It really highlights how lean is not just a simple checklist you hand to a supervisor. It is a fundamental rewiring of how a company thinks, how it acts, and how it allocates its most precious resource, time.
It requires a complete, painful paradigm shift from traditional mass production thinking to true lean thinking.
The shift is massive.
In mass production, the overall aim is simply to reduce cost and increase machine efficiency, often at the direct expense of everything else. In lean thinking, the aim is to eliminate waste and add customer value.
Huge difference.
In mass production, quality is an inspection step at the very end of the line, where you sort the good from the bad. In lean, quality is built into the DNA by design and methods. In mass production, improvement is an expert-driven, periodic event. In lean, improvement is worker-driven, daily, and continuous.
All right, we have covered the core philosophy, we have dug through the toolbox, and we have survived the implementation nightmares.
We've covered a lot of ground.
We have. And it is time to transition into the final phase of our deep dive. You know, while I was researching this topic, I spent a lot of time browsing engineering forums and subreddits, and there are massive heated debates going on about lean. People have very strong opinions.
Oh, I'm sure they do.
So, I'm going to act as the voice of the internet here. pitching the most common, hotly debated questions that engineering professionals are arguing about online right now. Are you ready to tackle the forums?
I am absolutely ready. Let's hear what the internet has to say.
The first, and arguably the loudest objection I see online is this. I work in low-volume, highly complex aerospace engineering. Lean seems great if you are Toyota making 10,000 identical sedans a day. But can Lean actually survive, let alone work, in an environment where we are building small batches of incredibly complex, highly variable systems?
It is the most common objection by far, and the answer is absolutely, unequivocally yes.
Really? Even for low volume?
Yes. The fundamental misunderstanding here is that lean is about high volume. It is not. Lean is about flow and waste elimination, regardless of volume.
Could prove it.
To prove it, let's look at a stunning historical example. The Iridium deployment. This was a massive project to launch a constellation of complex, low Earth orbit satellites.
Satellites, definitely low volume.
Very complex. Using lean engineering principles, they achieved a manufacturing cycle time of just 25 days, compared to an industry standard that typically ranged from 12 to 18 months.
Wait, let me make sure I heard that correctly. They took the cycle time from over a year down to 25 days for a space-rated satellite.
Yes, and they achieved a dock-to-dock rate of 4.3 days. And the actual deployment phase was even more astonishing. They successfully launched 72 highly complex satellites in 12 months and 12 days.
That is absurdly fast.
At one point, utilizing heavily synchronized lean logistics, they launched 14 satellites on 3 different launch vehicles from 3 different countries in exactly 13 days. They achieved 22 consecutive successful launches.
Wow.
That is highly complex, extremely low-volume aerospace engineering executing at a level of precision and speed that traditional mass production could never dream of.
I've got another incredible aerospace example from the source materials to back you up on this. The JDAM project, the Joint Direct Attack Munition.
Yes, another great one.
This was a program to convert unguided freefall bombs into accurately guided smart munitions. The financial impact of Lean on this program was staggering. Listen to these numbers closely. By utilizing lean engineering to ruthlessly focus on creating product value and eliminating waste, unit costs were reduced greater than 75%.
75% reduction in unit cost on a complex military munition is virtually unheard of in traditional defense contracting, where costs typically spiral out of control.
And the absolute savings are mind-blowing. The total savings on the project were greater than the mathematical amount 2.9b.
That's a massive number.
Huge. They took the original cost estimate and dropping the original estimate from the mathematical value 68 plus K down to 15K per unit. That is the ultimate definition of doing the right thing right. It absolutely, without a shadow of a doubt, works in complex, low-volume aerospace.
The math doesn't lie. Okay, what is the next big debate from the forums?
Here's a question that comes up a lot, especially with younger engineers entering the workforce. Does lean intersect with green environmental design? Or does lean's absolute obsession with speed and cost reduction actually hurt environmental sustainability by encouraging corner cutting?
That is a very modern concern, but the reality is they are deeply, inherently interconnected.
Practically, how so?
In fact, a lean to green outlook is a core pillar of the modern lean engineer's foundation. Think about the philosophy logically. Lean is entirely focused on the relentless elimination of waste.
Right.
Waste is, by definition, an inefficient use of resources, whether that is physical materials, electrical energy, factory space, or human effort. By eliminating waste from your process, you are inherently and automatically reducing your environmental footprint and environmental risk.
Can you give us a tangible, physical example of that intersection? Where does lean logistics actually meet environmentalism?
Let's look at the Saturn Automotive Manufacturing Plant in Spring Hill, Tennessee. They implemented a massive plant-wide Kanban system.
Kanban.
A Kanban is a visual signal, often a physical bin, a card, or a digital trigger, that signals the production or movement of parts in a pull system. Saturn arranged to receive more than 95% of its parts from its suppliers in custom reusable containers.
So they completely eliminated the cardboard boxes, the single-use plastic wrap, the wooden pallets.
Exactly. These sturdy, reusable containers served as the physical Kanban signals themselves. When a bin on the assembly line was empty, it was sent directly back to the supplier, physically signaling them to make more parts to fill that specific bin.
That's incredibly elegant.
This seemingly simple lean logistics tool eliminated literally tons of packaging waste every single year. It also drastically reduced the physical warehouse space needed to store that waste, and the massive amount of energy required to manage, compact, and dispose of it.
That is a perfect synergy. Operational efficiency directly drives environmental sustainability.
And it goes much further than just cardboard packaging. Because Saturn was rigorously implementing lean production systems, they dramatically improved their first-time quality on the vehicles.
Meaning they didn't have to fix mistakes later.
Right. When you build the car right the first time and you don't have to rework or repaint defective cars at the end of the line, your raw material usage plummets.
Paint is a nasty chemical process, too.
Exactly. Specifically, the source notes that those operational quality improvements directly led to a massive reduction in paint solvent usage by 270 tons between 1995 and 1996 alone. Lean methods naturally and effortlessly align with the strict preferences of environmental regulatory agencies by reducing energy inefficiency and decreasing the sheer complexity and material usage in consumer products.
Okay, we have one final question from the internet, and this is a big one regarding the daily reality of modern engineering work. In the age of globalized teams, remote work, and massive corporate campuses, how do we actually bridge the gap between the isolated engineering design office and the physical, chaotic shop floor where the thing is actually built? How do we stop engineers from just designing something in CAD and throwing it over the wall to manufacturing to figure out?
That is the ultimate crux of concurrent engineering. The answer lies in a combination of physical proximity, whenever humanly possible, and the rigorous mandatory application of modern digital simulation tools.
Physical proximity.
Management has to ask themselves constantly, are design, engineering, and production making plans to physically move closer together? Is there enough room on the factory floor for the manufacturing engineers to actually see what they have designed being built in real time?
Physical proximity is huge, because if the design engineer has to literally walk past the final assembly line every single day to get to their desk, they are going to notice very quickly if their design is causing the assembly workers to struggle, curse, or reach for a shim.
Absolutely. The feedback loop is immediate. You can't hide from a bad design.
Right. But what if they aren't close?
Well, when physical proximity isn't possible because, say, the design office is in Seattle and the factory is in another country, we must rely on deeply integrated digital design tools. And there is a hard, unbreakable rule in modern lean engineering that bridges this exact gap.
Okay, what's the rule?
The rule is this. An engineer's job is not done until we have successfully conducted a 3D production simulation.
Let me repeat that for everyone listening, because it is vital to the fuzzy front end.
Yeah.
Your job as a designer is not done until the 3D production simulation is successful.
Right. You cannot just design the brilliant part in a 3D solids-based mechanical program, save the file, and call it a day.
Throwing it over the wall.
Exactly. You have to virtually, digitally build the entire factory environment around it. You have to map the robotic arm movements. You have to simulate the human ergonomics. Can the worker actually reach the bolt with a wrench without straining their back?
Oh, wow.
You must mathematically prove that the part can flow through the entire value stream without interruption or collision. You have to virtually build the factory before you ever physically build the part.
It forces you to think about the manufacturing steps.
Yes. This total digital integration drastically reduces the wastes of complex handoffs, waiting on physical prototypes, and downstream rework, and it dramatically increases first-time quality.
Okay, let's unpack everything we've covered today.
It's a lot.
It is. So what does this all mean for the working engineer listening to this right now? As we bring today's deep dive to a close, I think the grand takeaway is that lean engineering is not just a checklist of Japanese vocabulary words to memorize for a management meeting.
Definitely not.
It's not just a specific U-shaped layout for a factory floor. It is a profound, holistic lens through which the entire life cycle of a product, from the very first spark of an idea in an engineer's mind, through the thousands of micro decisions in the CAD software, all the way to the product's ultimate environmental disposal, is viewed, scrutinized, and optimized.
That's perfectly said.
It is about taking the time and the discipline to write perfect, robust DNA so that the manufacturing organism can actually thrive.
I agree completely. It is a philosophy of total system health. And I want to leave you, the listener, with a final, somewhat provocative philosophical question to ponder long after this session ends.
Oh, lay it on us.
We have established today that lean engineering is ultimately about the relentless, uncompromising elimination of the waste of human effort to allow for pure, unhindered value creation.
Right.
But if we follow that trajectory to its logical, absolute conclusion, What if the ultimate goal of lean isn't just a better aerospace component or a faster assembly line or a cheaper consumer product?
What else could it be?
What if the true endgame of this methodology is evolving the human mind itself to instinctively think in perfect, frictionless systems? As we strip away the chaos, the waiting, and the mindless rework of our daily workflows, are we merely leaning out the physical product, or are we fundamentally leaning out human cognition itself, preparing our collective intellect to solve the seemingly impossible engineering challenges of the next century?
That is an incredibly deep, resonant thought to end on. And that level of exploration is exactly why we dive into these topics. If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.